Let's compare circuit analysis with complex frequencies to our sinusoidal steady-state circuit analysis. Let's assume we have a voltage source, a sinusoidally exponentially varying sinusoid. So we have a cosine of omega t with a phase shift, and it's exponentially varying with a damping frequency of sigma. So by Euler's identity, we can take that our e to the plus or minus j alpha, our general Euler's identity, that's our cosine alpha plus or minus j sine alpha, where cosine alpha is the real part. So our cosine alpha is the real part of e to the plus or minus j alpha. If we substitute in here for the j alpha, what we have is a j omega t, in parentheses, omega t plus theta. So our cosine omega t plus theta is the real part of this. So remember, that's what we started with when we were looking at just sinusoidally varying functions as well. So if we have our Vm e to the sigma times the real part of e to the j omega t plus theta, or it could be, remember, we could have plus or minus the radiant frequency. So our exponentially varying function we could represent as either of these two functions, where here we have a frequency of sigma plus j omega t. Here we have a frequency of sigma minus j omega. So I shouldn't say the t, just plus or minus j omega. Or we could take that, our exponential function, instead of writing j omega t plus theta, we could write it as two separate functions. So we break out just the frequency in this exponent, and here we just have the j theta, so that's our either of these two functions for s is equal to sigma plus j omega, or s is equal to sigma minus. So this is the pair of complex conjugate frequencies associated with our exponentially damped functions. So we still have, so if we look up here, we still have our Vm and theta, right? That was our phasor. If we were going to take this and when we didn't have the e to the sigma t, if we just had a sinusoidal varying function, we'd say our phasor was Vm angle theta, or e to the j theta. So here's our Vm e to the j theta, our Vm e to the j negative theta, where this theta is associated with a positive frequency omega. This one's associated with a negative frequency omega. Remember, we said we want to use the positive frequency omega. So again, if we compare that to our chapter 10, what we said there was we took the real part of our Vm e to the j theta e to the j omega t. Our frequency was just a radian frequency omega. We didn't consider the plus or minus omega there. And we didn't realize that was actually an imaginary part of our complex frequency. But here was our phasor. If we can substitute in our s is equal to sigma plus j omega here's what we have is we can substitute in our s. So we have similar functions where what our voltage, our time domain voltage, is the real part of this. So here's our phasor and here's our frequency. So here our frequency is sigma plus j omega. It's really we know when positive j omega exists, we must also have the negative j omega. So comparing that again to chapter 10, what did we do in chapter 10? Well, we took we started out by omitting the real part, and we just assume it. So we just assume the real part, and then we suppressed e to the j omega t. So now we'll suppress e to the st, and then we just did our circuit analysis with phasors, where our Vm angle, we used theta typically for voltages and phi typically for currents, just to distinguish. And then in the end, we reinserted the e to the st, took the real part of the solution, and the real part of the solution gave us our cosine. That's why we always use cosine functions. So if we look here at this example, we have an RLC circuit with a voltage source forcing function. That voltage source forcing function, we should give this a unit. That unit is volts. So that's e to the negative 2t cosine 4t plus 10 degrees volts. We want to know what are the two frequencies, what are the two complex constants, what's our amplitude Vm, and then what we want to find is the current in this circuit. So the current, we know, must have the same form, or we'll assume it must have the same form, and it's going to have the same frequency, -2 plus J4. We want to know the amplitude and the phase shift. So if we want to find the complex constant, then what we need to do is we need to use our Euler's identity here, right? So just to give myself a little bit more space, I will erase our unit, and here, so if we're going to end up with, get my pen working, equal to our 60 e to the -2t, and we'll take that cosine function and we'll represent that as our e to the j 4t plus 10 degrees plus e to the -j 4t. Then we have to do our minus 10 degrees there, and we'll put that all goes over 2, right? So our complex constant k, that's going to be equal to our 30, 60 divided by 2, and that e to the j plus or minus 10 degrees, right? So we have 1 and 2, and our frequency s here, that's equal to our -2 for sigma, but we do end up with our plus or minus J4, right? So that's going to have a unit of per second, and fix that so it's the degrees. That's, since we said this has a unit of volts, that also has a unit of volts. Whereas our amplitude, that's 60, right? So remember, that's 260, which is equal to 2 magnitude of k. So now what we need to do, so that's review, but now what we need to do is we need to find our current phasor and our current amplitude and our current phasing. So let's give ourselves a little bit more space where we have we can represent our sinusoidal, exponentially damped sinusoidal varying function as a sum of two complex frequencies, complex exponentials, with complex constants as their amplitude or coefficient, which is going to be the real part of either of these two. And we'll give ourselves some space. Our frequencies we found, -2 plus or minus J4, where S1, this is S1, our S2 is S1 conjugate, and we have a K1 and a K1 conjugate. If we just look at K1, that's our 30 e to the j theta. That's associated with, j theta 10 degrees is associated with the positive 4 radians per second. Our voltage phasor then is 60 angle 10 degrees. So we can write that instead of complex exponential form, just in this easy notation phasor form to make it look easier. Our current then is the real part. What we need to find is our Im and our phi, we have the e to the st, and our voltage is the real part of 60 e to the j 10 degrees e to the st. So if we can write that in phasor form, pull out our Im angle phi, the real part of e to the st, our voltage phasor, pulling out our phasor, and then it's going to be the real part of the e to the st. Or we can write that, what we said, our bold font represents a phasor, where it's a complex number in magnitude angle form, where we're representing a current here. So here we have our current in time domain that has the phasor, and we're taking the real part of that complex exponential. So what we want to do here is we want to write a loop equation. So we can write a loop equation. We have a voltage source. We know the form of our current. We're looking for that current phasor I. We know the frequency, -2 plus J4. So writing that, our loop equation, V of t is equal to Ri L di dt, 1 over c integral of I dt, if we just use the use this form of our integral. So when we do the di dt, that's L is 3, we're just plugging in numbers, R is 2, and 1 over 0.1 is the 10. So that's a per farad for a unit. And then what we want to do is just substitute in for I, our I e to the st, and we can substitute in for V, what we know for V of t, that's our 20. That was given up here, right? It's given here. We substitute those in. When we substitute them, there's our voltage, there's our 2 times our current. When we do the di dt, we end up with 3s, right? So we still have this complex exponential, and that's what we found when it was just j omega t. Our L, we said that impedance was j omega L. Now our impedance seems to be Ls. And here we have, when we're integrating, it's 1 over s, right? So we integrate the e to the st, we end up with 1 over s, just like we ended up with 1 over j omega c when our frequency was just a radian frequency, times our I e to the st. So again, what we're seeing is this, where we're substituting it, if we substituted in for s just j omega, if sigma was 0, that's our sinusoidal steady state. So then what we do, we just suppress the e to the st, and when we're working just in frequency domain, we don't want to have a phasor multiplied by time domain. So we suppress that, and here we have just our frequency form or our phasor form of our KVL loop equation. Excuse me. So this is entirely in frequency domain. We don't have a variable t in this equation. We've suppressed it, and we will be able to use this approach. So now we have, if we want to solve for current, we have this I, we need to divide out our 2 plus 3s plus 10 over s, and we can solve for that I as a general equation, but we know what s is. S is negative 2 plus j4. This is just like when we knew the radian frequency, we could plug in for what omega was, and we can take that, plug in our negative 2 plus j4, 10 divided by negative 2 plus j4, and we can solve for that. Hopefully you can solve for that quickly in your calculator, and we get 5.37 with an angle of negative 106.6. So our amplitude of our current is 5.37, our phase shift are negative 106.6 degrees. So then what we want to do is we want to then convert that to taking the real part, right? We convert that to time domain. So our time domain, that's our Im, e to the sigma t cosine omega t plus phi, plugging in what we solved for, and we have our current. So this example shows you how we can work in the S domain. We solve for our currents in the S domain. It's just a subset of what we did with sinusoidal steady state. It's just a subset of that, where our S, we used S was just equal to 0 plus j omega. All right, that's it for this video.